All right, so let's look at a few more of these shear moment diagrams. How far did we get? We got to this distributed load. We didn't get to the distributed load with the extra point load on it, though, is kind of what I recollect. Is that correct? We didn't. This is where we need to be. Right there. Okay. So let's kind of keep going with this stuff. We're just getting into, more and more varied diagrams here. So on this one, we got the distributed load with a point load 8 feet over from the left. Notice the reactions are a little bit out of balance because of this load right here is offset. It's not in the middle, it's off to the right. So that puts more of a reaction on the right. Okay, so to get a shear diagram, you start at 0. These diagrams always start at 0. It'll kick up right there, and it'll kick up to 21. Then it will drop by an amount equal to the area under the load diagram. So what we have there is we have negative 3 kips per foot times the 8-foot distance. See, I'm going to take it just out to that load because I know right where that load hits, there'll be a big change in shear. So it helps, it's easiest if I get the area on either side of that. That just makes it easier to plot what I'm trying to do there. So that's why I'm doing this. So I'm going to go ahead and calculate those, and that'll be 24 and minus 12. So what's happening here is I'm starting out at 21 on the left, then I'm going to drop by 24. So I'm at 21 and I drop by 24, and where I end up is negative 3. So that's the value there on the right. Then I'm at negative 3 and I drop 9 more, so negative 3 minus 9 is minus 12. So that's where that value comes from. Okay, then I'm at negative 12 and I drop by the area, so that's 12 more, so I end up at negative 24, and then I've got that reaction there that takes me back up to 0. These things should always close to 0. So negative 24 plus 24 is 0. All right. So there you go, there are the numbers. Got any questions on that one so far? Get to that shear diagram. Now the next thing that you'd want to do then would be to come up with the areas of the shapes. Okay, whenever you see shapes, you want to get areas on these. So that would be the next thing to do. So I'll get the area on the left. It's 1/2 times the height of 21 times the base of 7, 73.5. And then I've got 2 shapes there on the right. I've got that little triangle. And what that does is go from 0 to negative 3. So that has a height of negative 3 and a base of 1. So 1/2 times negative 3 times 1 is negative 1.5. That's that little triangle. Then I've got a trapezoid. I need to find that area. Now the way you can do that is on a trapezoid, you're going to have 2 different heights. You can kind of cut it right in the middle, kind of get a point in the middle there, cut a triangle off of that and just flip it and pop it into the other side. So like that. And what that gets you is a rectangle. The height of the rectangle is the average height, h1 plus h2 over 2. And the width of the rectangle is the base b. So one way to get the area of that trapezoid is to take the average height, so that would be negative 12 minus 24, so that's the height on the left and the right, over 2, times the base of 4, and that'll be an area of negative 72. All right, so that's what's going on there. All right, so now I can get to that moment diagram then. So what's happening, like all diagrams do, it starts at 0. then it'll go up by 73.5. So it starts at 0 and it goes up to 73.5. Then it goes down just a little bit, just 1.5 down, and that gets it to 72. So it's hit its peak at 73.5, then it drops slightly. Now notice the value of shear where it hits 73.5 is 0, which is the slope of the moment diagram. So just as you learned in calculus there, at the maxima you've got a slope of 0. That's what's going on there. From there, you've got that, you're at 72. You've got the area here of negative 72, so that'll drop you back down to 0. Okay. Now the slope at the top is 0. The slope on the far left is equal to the value of the shear. It's 21. And the slope on the right is equal to the value of shear, which is negative 24. So it goes up with a slope of 21, tops out with a slope of 0, and then comes down with a slope of negative 24. So that's concave down, I think is what that is. Okay. So that's the shape. So we okay with that? Okay. So we're just going to go through a few of these, just kind of get the rules figured out and how you create the diagrams. So good with that? Okay. All right. Now on the next page we got some more. So the first one, we got a distributed load with a couple. All right. Now what that couple does is it takes that beam, it pushes the left side down and tries to lift the right side. So what that does is kind of tweak the reactions, kind of offsets things to the left. We got more of a reaction on the left now, it's 24. So when we get to the shear, we start at 0, we go up to 24. Then we're going to drop by 3 kips per foot, okay? Now, let's see what that's going to do. Now, dropping at 3 kips per foot, we're at 24 kips. We're going to drop by 3 kips per foot. That means we're going to hit 0 8 feet over. So if I take that value, divide it by the slope, I'll get when it hits 0, basically, when the height will be 0. It's 8 feet over. Okay. Now the other thing I'm going to want here is an area. And that area, that whole thing is, again, that's negative 3 kips per foot times 12 feet. So that's negative 36 kips. So I'm at 24. I'm going to drop by 36, and I'm going to get to negative 12. That's what's going to happen. So you notice that diagram looks a lot like the distributed load on the previous page, except it's kind of just shifted, basically, on account of that couple. That shifts things over. Okay, another thing about that is that couple has no direct effect on the shear diagram. There's no discontinuity or change at the shear diagram there. Couples don't affect load and shear directly. Okay. Now it is going to affect the moment, though. So what I'm going to want to do here is I'm going to go, okay, I've got this couple 5 feet over. If I'm at 24 and I'm going to drop by 3, and I'm going to do that over a run of 5, that's going to be 24 minus 15. That's 9. That's the value there at 5 feet. Okay. So those are the things that I start to look at when I start building this diagram here. So are we doing all right with that? We got any questions so far? So good. Okay. All right, so I got the area there, and then I got kind of what happens there with the shear diagram. It goes from 0 up to 24, drops 3 kip per foot, so I hit 0 at 8 again. and then it ends up at negative 12. And when it ends up at negative 12, this 12 kip reaction just pulls it back up. All right, now the slope of that line is negative 3 because that's the value of the distributed load. Okay. All right, now what I got to do here next is find areas. All right, let's do that next. See, I've got that line I want to draw at 5 feet over because I know there's going to be a discontinuity in the moment diagram at that point. That's why I'm drawing that red line in there on the shear diagram right here, because I want to find the area of that trapezoid on the left. The average height of that is 24 plus 9 over 2, which I think is 16 and a half times 5, which would be whatever, 82 and a half, I think. Yeah, 82 and a half. That's the area of the trapezoid on the left. Then I've got a triangle, 1/2, 9 over 3, 13 and a half for the triangle. So there we go. And then I've got an area on the left of negative 24, right there. Okay. So those are my areas. So what's going to happen then is the moment is going to start at 0. It's then going to go up to that first area, which is 82 and a half. That's on the left. So I go from 0 up to 82 and a half. Okay, the slope there starts at 24 and then it's at 9. So it's getting less positive, so that's concave down. Now, as soon as it gets to 5 feet and 82 and a half, it feels this couple right here. Now, what that couple is like that. That's a positive. So that's plus 72. The effects on the moment diagram, though, it's negative 72 as far as its effects on the moment diagram. Okay. So what's happening there is the moment diagram's up at 82.5. It drops by 72. It ends up at 10 and a half right there. So the moment diagram's down there at 10 and a half, and then it just kind of keeps doing what it was doing before. See, what this is here is parabolic. It's going to keep in that parabolic shape. It's just been shifted down by 72. So that couple changes the moment diagram immediately. And it changes it with the opposite sign with which it's applied. So that's a positive 72. It affects the moment diagram with a negative 72. So that drops by 72 down to 10 and a half. Well, then you got this area right there, 13 and a half. So that gets you up to 24. That's where the slope's 0. That's the maxima, or local maxima, you might call it. And then it drops by 24, so it comes back to 0. Okay. We got any questions on that? All right. So that one shows the effects of that couple. It affects the reactions, and that has an indirect effect on the shear diagram. And it also affects that moment diagram. It puts that vertical line in there, that offset. You got to remember to change the sign on the moment diagram when you have these couples, because what's happening for the beam is the beam's like so. You've got this counterclockwise couple that appears. So what the beam does is react to it. Okay, so that's positive 72. What the beam does to balance that out is come back with a negative 72 change in moment. That's what's happening there. That's why the sign changes. Now that doesn't happen with shear and a load, because that funny sign convention on shear where shear is positive down, that kind of washes that sign flip out. which is kind of handy because these come up more with loads and shear than they really do with moment. They're a more common situation. But with moment, you got to remember to flip the sign. Shear, you don't need to worry about it. Moment, you do. Okay, we all right with that one? Okay. So you end up with something like that. So getting a little busy with some of this stuff, to work all this stuff out. Whenever I see shapes, I calculate areas is what I do. Okay. All right. Okay, we got a cantilever for the next one. Now a cantilever is different, that it has a couple reaction over there at the wall. There it is. We've also got an area there, so let's go ahead and calc that up. So that area there is 48. So this area here is 8 kip per feet times 6 feet. It's 48 kips. Kip, remember, is 1,000 pounds. You've got a force reaction and a couple reaction there at the wall. So what's going to happen here with the shear diagram is you're going to go from 0 up to 48. So that's 0 plus 48. After that, there's no change in slope. Slope is 0. So it just carries over to the wall at 48. Then you've got this reaction that just pushes you right back down. Okay. So there's the shear based on that loading diagram. This one is kind of funny. That loading diagram pushes up, is what it does. You see the arrowheads are up, so that's why it's a positive area. Okay. Now what you want to do next is find the area under the shear diagram. Okay, that would be the next thing to do. Okay. So I want to find those areas. So we've got a triangle, 1/2 by 48 by 6, and then 48 by 6. So 144 and 288. And now what that does there on the moment diagram is you start at 0. You increase by the area of that triangular area on the shear, so that gets you up to 144. And then you increase the second time by 288. So 144 plus 288 is 432. So you get to a moment value at the wall of 432. There's a positive couple reaction there, a moment reaction, a couple reaction. So you flip the sign, and that takes you back down to 0. And that's always a good check on these. The reaction should always come out to be 0 on these things. All right. So there's the load to shear to moment on this. So we got any questions on that? All good? Mm-hmm. Oh, let's see here. So let's pause this for a second. All right, so here's the homework. Whoops, homework that's coming due. So 332 and 3, and then 341, 2, and 3. We'll finish up 341, the material for that tomorrow. Okay.